In section 13.3, we introduce partial derivatives, which provide instantaneous rates of change of a function in the direction of the x, y, and z coordinate axes. We would like to expand this concept so that we can find instantaneous rates of change in any particular direction, not restricted to the coordinate axes. So this brings us to the notion of a directional derivative. We're going to assume, first of all, that we have a function of two variables, f of x, y, and we also have a unit vector composed of the components u1 and u2. I want to really bring your attention to the fact that it's imperative that this vector is unit. So if we would like to find the directional derivative in the direction of u, specifically at some point x naught, y naught, then we denote it by this capital D with a subscript u of f, and it's defined to be the following. We're going to take the derivative with respect to s of x, evaluated at our point x naught, y naught, but then shifted some su1 and su2, where remember u1 and u2 are just the components of your unit vector. And then all of this is going to be take the derivative and then evaluate at s equals 0. And this is all assuming that this derivative exists. So this first half of the definition is defining the directional derivative for functions of two variables. And then of course we just have here the following definition with three variables, adding that third component function in. All right, now very similar to what we talk about in Calc 1, when we introduce the derivative, we compute it via a limit of the difference quotient. And it can be very tedious, very time consuming. And then we quickly learn techniques of differentiation so that we don't have to go through that process anymore. The same holds true with directional derivatives. We can compute directional derivatives using these two formulas given here in the definition, but as it turns out, it's really just a lot of work to do it that way, and so the theorem below will give us a shortcut here. But before we get there here, how do we interpret the directional derivative geometrically? So as I stated at the beginning, the partial derivative gives you the instantaneous rate of change in the direction of the coordinate axes. The directional derivative gives you the slope of the surface of the function, f of x, y, in the direction of u at that particular point. So again, we're no longer restricted to looking at the slope of the surface in just three directions, the coordinate axes. Now we can pick any unit vector we want, and we can look along that direction and find the slope of the surface at that point. All right, so this remark is just saying what I said earlier, that this previous definition is rather tedious, and so that brings us to this theorem. Theorem 3 says that if you have a differentiable function at a point and if you have a unit vector, then you can find your directional derivative by taking your partial with respect to x times the x component of your unit vector and then adding it to the partial of your function with respect to y times the second portion of your unit vector, all the while evaluating at the point in question that you would like to look at. And so the same holds true for functions of three variables, adding in this third summand here for the directional derivative. So let's jump into some examples of computing the directional derivative. Starting with problem 6, we want to find the derivative of f at u at the specified point P. All right, so we have our unit vector given to us. You can assume that if your vector is labeled as u, as its name, that it is a unit vector. If it is labeled by anything other than u, the book does not assume it's unit, and you should go through and either check that it's unit or normalize it to make sure that it is unit. So let's move forward here. What I'm going to do first is find the general directional derivative. And so I'll write that as at x, y, z. And I'm going to start by taking the partial of f with respect to x. So this y is just a coefficient. The chain rule here on the exponential is going to pop a z out front. So this is going to be yz e to the xz. And then of course the plus z squared is going to go to 0. I'm going to multiply this partial derivative by the first component of the unit vector, which is 2/7. And now I'm going to move on to the partial with respect to y. That just gives me an e to the xz. Again, the z squared goes to 0. And I'm going to multiply by -3/7. And then finally, I'm going to take the partial with respect to z. That's going to pop out an x. ye to the xz, and then the second term is going to give me 2z, all of this being multiplied by 6/7. So this is my general directional derivative, but in the direction of the unit vector u. I would like to evaluate this at the point 0, 2, 3. So I'll plug those values in for x, y, and z. All right, so what I get here is 6e to the 0 times 2, 6 plus e to the 0 times -3/7 plus 0 plus 6 and then this is times 6/7 here. All right, so what do we have? We have 12/7 plus a -3/7 plus 36/7 gives me 9 plus 36, which is 45/7. All right, so again, the interpretation geometrically is this is the slope of the surface z equals ye to the xz plus z squared, particularly at the point 0, 2, 3. But remember, there's 360 degrees of rotation around that point. In which direction are we looking at our slope? Because this is no longer a curve that's going to have the same slope. It's going to change with the direction. So this is in the direction of the vector u. All right, so that's our geometric interpretation of what that scalar value means. All right, 14 is a similar problem. We want to find the directional derivative of f in the direction of a. And so I just want to kind of underline this. This is in the direction of a, but you can notice here at a glance that certainly this vector a is not unit. So the first thing that I'm going to do is I'm going to find the length of this vector. So that's going to be the square root of 25 plus 4. So this vector has a length root 29. And so what I'm going to do is I'm going to normalize it to find a unit vector. So u is going to be 1 over root 29 times that vector a, which is 5, -2. All right, so now that I've normalized this vector, I can proceed by finding the directional derivative exactly as I did in 6. Let's start by finding it in generality, and then we will evaluate at our particular point. Oh, and this is just a function of 2 variables, so I can leave off z. All right, so first let's find the partial of f with respect to x. That is e to the y minus ye to the x. And then I'm going to multiply by the x component of my unit vector, which is 5 over root 29. Similarly, I'm going to take the partial with respect to y, which is x e to the y minus e to the x. And I'm going to multiply by the y component of my unit vector, which is a -2 over root 29. Finally, I'd like to evaluate this directional derivative at the point that I care about, which in this case happens to be 0, 0. So this becomes 1 minus 0 times 5 over root 29 plus 0 minus 1 times a -2 over root 59, let's do 29. So this is a 5 over root 29. Double negative here makes plus 7 over root 29. Whoops, I'm ahead of myself here. 2 over root 29. And so my final answer is 7 over root 29. As always, you're welcome to leave a square root in the denominator. No need to rationalize, but that works just as well. All right, so our next remark is just recalling that back when we introduced vectors in chapter 11, we said if we were working in 2 dimensions, that is for vectors in the xy plane, that we could express those vectors in terms of sines and cosines. Specifically, if we're working with a unit vector, then our weights in front of sine and cosine are both 1. So we can write unit vectors in terms of cosine theta and sine theta of an angle, and of course using the I and j notation as well. So in this particular setup where we're writing our unit vectors in terms of sine and cosine, we can then express our directional derivative in this format as long as we know the angle theta from the positive x-axis to our vector. So let's take a look at this example, number 20. Find the directional derivative of f at p in the direction of a vector making a counterclockwise angle of theta with the positive x-axis. All right, so let's dig in. Finding our directional derivative in generality, and then we'll plug in later. And darn it, I really want to make these functions of 3 variables, but they're not, so we'll stick with 2. So first, let's find the partial of f with respect to x. I'm going to apply the quotient rule here. So here's my bottom times the derivative of the top minus the top times the derivative of the bottom. And this is all over the denominator squared. And then I want to multiply by cosine of pi halves. Now, cosine of pi halves we know to be 0. So this whole term drops out to 0, and I didn't even really need to calculate that derivative. Next, let's take the partial with respect to y. So bottom times derivative of the top minus the top times the derivative of the bottom, all over the bottom squared. And then this time we want sine of pi halves, which we know goes to 1. And so let's simplify here. I get a negative x minus y minus x plus y all over x plus y squared. And so this whole thing simplifies to a negative 2x over x plus y quantity squared. Now, in our particular case, we would like to evaluate this at -1, -2. So on top, I get a positive 2. On bottom, I have -3 squared, which is 9. So my directional derivative is 2/9, or again, geometrically, this is the slope of the surface defined by x minus y divided by x plus y in the direction of, in this particular case, this happens to actually be the y direction, and then all evaluated at the point -1, -2. All right, so next we'd like to introduce the gradient of a function. The gradient is actually an operator that inputs a multivariable function and outputs a vector. And it can input any degree of a multivariable function. That is, you can take a multivariable function that has 3, 4, 10, 1,000 variables, and it's going to output a vector that lives in the same dimension as the number of variables in your function. So let's take a look here. The gradient is denoted by this upside down triangle here. So kind of like delta, but delta is a normal triangle. I will pronounce this as del rather than delta. So del f of x, y here is the partial of f with respect to x in the I hat coordinate and the partial of y with the partial of y in the j hat coordinate. And then again, we just have a third dimension here if it's a function of 3 variables. I really want to emphasize here that the gradient is outputting a vector. So a lot of times I'll see students, they know to take the partial derivatives in each coordinate, but then they'll try to add them up or they'll do something else. So remember that those become components of a vector. All right, and so keeping in mind the definition of the gradient, we can now express the directional derivative as the gradient evaluated at our point in question dotted with our unit vector. And so personally speaking, I really like thinking of the directional derivative in this notation because it's easy to remember this formula, the gradient dotted with the unit vector. So let's get some practice working here with gradients. We want to find the gradient for W. So remember, the gradient is just the vector whose component functions are the partial derivatives in each coordinate. So let's write our gradient for W. First, I want the partial with respect to X. That's going to give me e to the 8y sine 6z. Next, I want the partial with respect to y. The chain rule will kick out an 8 in front, so I get 8x e to the 8y sine 6z. And finally, the third component is the partial with respect to z. So the chain rule is going to kick a 6 out front. I get 6x e to the 8y cosine 6z. And this right here is my gradient. There's really no further work to show. It's just calculating those partial derivatives of each coordinate. 44 is more the same, but then just one added step of evaluating the gradient at a specified point. So let's begin by finding the gradient at any general point. So I'm going to take the partial with respect to x. So I'm going to pull this exponent down in front. Don't touch the inside. Subtract by 1 and then multiply by the derivative of the inside. But again, this is with respect to x right here. And then I get almost the same thing for y. The only change is my inner derivative becomes a 2y instead of a 2x. All right, now you're certainly welcome to cancel out your 1/2 and 2 since they simplify to a 1. And if you find it easier, you could write this as fractions x over, in this case, x squared plus y squared to the 3/2, and similarly in the y coordinate. All right, so now we would like to evaluate it at the point. So I want to find the gradient of f at 3, 4. So this becomes 3 over the square root of 9 plus 16, then cubed, and similar over here. All right, so 9 plus 16 is 25. The square root of 25 is 5, and 5 cubed is 125. And whoops, and I just forgot my negative sign, so let's go back in there in red and add those in. So those are coming right here. I just dropped them when I copied down. And so for my final answer here, I'm getting negative 3 over 125 and negative 4 over 125. And this is my directional derivative for this function at the point 3, 4. All right, theorem 6 of this section says the following. Assume that you have a function of two variables that has continuous first order partials in a disk centered at some particular point x naught, y naught. And suppose that the gradient at that point is non-zero. Then the gradient at that point is normal to the level curve of f at that point x naught, y naught. Okay, so this is giving us a geometric interpretation of the gradient and how it is positioned according to the level curve. So let's look at a particular example here. Sketch the level curve of f of xy that passes through the point and draw the gradient vector at P. All right, so what we need to do first of all is just recall what a level curve is. Level curves occur when you replace z, or in this case f of xy, with some constant k. All right, so the first question is, what is that constant k that corresponds to the point negative 2, 2? So if I evaluate this at the point negative 2, 2, what I'm getting here is 2 over 4, which is 1/2. So this tells me that I am looking at the level curve for k equals 1/2. All right, so that being said, I now know that my level curve is 1/2 equals y over x squared. So if I want to plot this level curve, typically we solve for y, and I get y equals 1/2 x squared. So let's accurately sketch this on the grid here provided. So we have 0, 0. If I plug in x equals plus or minus 1, I'm getting out 1/2. If I plug in plus or minus 2, I'm getting out 2. And if I plug in plus or minus 3, I'm getting out 9/2 or 4.5. All right, so go ahead and sketch in that parabola. All right, so here's our level curve for k equals 1/2. So now what we would like to do is draw the gradient vector at that particular point. So let me just highlight that point here that we care about. It's at -2, 2, right here. So I highlighted it in orange. So now what we would like to do is draw the gradient at this point. Let's compute the gradient in generality first. Gradient of f of xy is the following. So when I take the derivative with respect to x, I'm going to get a -2y over x cubed. And when I take the partial with respect to y, I get a 1 over x squared. All right, so now if I evaluate the gradient at -2, 2, what I'm getting back is -4 over -8 and 1/4. So in other words, I have 1/2, 1/4. All right, so to make it stand out a little bit more, I'm going to sketch this in red. Again, I want to start at this point here on my parabola, and I want to draw it to scale. So I'm going to go over 1/2 on the x-axis, and I'm going to go up 1/4. So here's 1/2, here's 1/4. Looks to be about right here. All right, and as far as my accuracy goes, this does appear to be a right angle. So you can see that that gradient is directed perpendicularly from that level curve. So if you sketch the tangent line here, it appears to be perpendicular. All right, we finished this section with a final theorem, Theorem 5, which says the following. Let f be a function of 2 or 3 variables, and let p be some point, x naught, y naught. Assume that f is differentiable at p. If the gradient is 0 at p, then that means all the directional derivatives are 0 at p. All right, and this makes sense, right? Because the definition of the directional derivative is that you want to dot the gradient with the components of the with the vector u. And so if the gradient is 0, then everything zeroes out. So parts B and C are the ones that are of interest. Part B says that if the gradient is non-zero, then among all possible directional derivatives of f at p, the derivative in the direction of the gradient of p has the largest value. So let's highlight that. The derivative in the direction of the gradient of f at p has the largest value. And then this largest value is just the magnitude of the gradient at p. Part C is very similar, but just the opposite. So it says if it's non-zero, then the derivative in the direction opposite to that of the gradient at p has the smallest value. And then in this case, that value is negative, the magnitude of the gradient of f at p. All right, so instead of going through a process of trying to maximize or minimize the value of the directional derivative, we can just use this fact and compute the gradient and know that the max and min is going to occur in that direction. And furthermore, we know what the value is. So let's finish this section with a final example here. This is 59 from the text. Find a unit vector in the direction in which f increases most rapidly at p and find the rate of change of f in that direction. All right, so we're looking for how it increases most rapidly. So by the previous theorem, we know that that's going to happen in the direction of the gradient. So let's note that. By theorem 13.6.5, specifically part B, the vector will be in the direction of gradient f at point P. All right, so to begin, let's go ahead and compute the gradient of f. And we'll find it in generality. First, I need the derivative with respect to x, which just gives me 1 over z. Now let's take the partial with respect to y. The first term goes to 0. Second term becomes a negative 2z over y cubed. And then finally, when I take the partial with respect to z, I do need to take the derivative in both terms. So the first term is a negative x over z squared. And then the second term is a 1 over y squared. So now let's evaluate that gradient at the point that we're given, which is 1, 2, negative 2. So this is a negative 1/2, 4 over 8, and a negative 1/4 plus 1/4. So this reduces to negative 1/2, 1/2, 0. All right, so this is the gradient, and we know that the direction in which f increases most rapidly is in the direction of this gradient. All right, so notice in the statement here, we want to find a unit vector in which the function increases most rapidly. So let's check to see if this gradient vector is in fact unit. So finding the magnitude here, we get the square root of 1/4 plus 1/4 plus 0, which is the square root of 1/2, or if you want, you can write it as root 2 over 2. Okay, so it was not unit. So our unit vector that we're looking for is going to be 1 over root 2 over 2 times this vector. And so if we simplify, this is going to be negative 1 over root 2, 1 over root 2, 0. And again, I'm happy with you guys leaving radicals in the denominator. Certainly doesn't bother me at all. All right, so this is the first part. This is finding the unit vector that we were looking for. And then the second part says find the rate of change of f at p in that direction. Remember, that is just the magnitude of the gradient. So that is precisely this value. So this is the rate of change of f at p. And then u is our unit vector at which the function is changing most rapidly. So this concludes section 13.6 on directional derivatives. Next section is going to make heavy use of the gradient when we talk about tangent planes and normal vectors.